All right, ladies and gentlemen, quiz number 6 walkthrough. This was pretty simple. It wasn't too complicated. You had to make a lot of value judgments, but overall, not too crazy. So 6.2 here, you have a strong relationship because you just have, as the more that this increases, the more this decreases. So that's pretty strong. You don't have a flatness to it. You do have it here, but it's not complete. And no, you would not put a line through it because it's very curved. There's just no good way to put a line in there. Line would not fit through the data here either, right? Here you could put a good line in there. Here, yeah, you could put a good line in there. You could try in a couple of these. You could try here. You can try here a little bit. As far as a strong relationship, yeah, strong. So this is strong. This is strong. This is pretty strong. This is very, very strong. This is weak. This one is weak as well. And this is moderate. This last one, moderate. It's moderate because there's a lot more dispersion going on here than this one that is really, really tight along the line. Okay. So here, describe the relationship. It's linear, right? It's linear. You can put a good line in there. The thing, and it's strong, right? It's kind of clustered around the line, and it's positive because you're going up and to the right. The thing here is that it's a little bit of a fan shape here, right? So, there's not a good linearity there because it's just, there's that shape there. You have a lot more variance over here than you do towards the bottom. How would your relationship change if your weight was measured in pounds while the units for hip girth remain in centimeters? It wouldn't change. It would still be the same. Unless you change kilograms to something that would change the direction of their value, like multiplying it times -1, you would have the same. It would be exactly the same. You're just expanding it a little bit more because you have more units of pounds in 100 kilograms. You have about 212 pounds. I forget. So 220 pounds in 100 kilograms. So that's how that would change. Here we're asked to write out the linear model, and so the linear model would be the expected heart weight is equal to the intercept, negative 0.357, plus the estimate for beta 1, 4.034, multiplied by body weight. The body weight is your X, right? Interpret the intercept. So the intercept here means that it's somebody that weighs 0 kilograms. If body weight was 0 and everything else cancels out over here, their heart weight would be negative 0.357 grams. No such thing, because no such thing as somebody weighing 0 kilograms, right? Interpret the slope. Then the slope 4.034 means that for every 1 kilogram of increase, you are going to have an increase of 4.034 grams. That's the slope. And the correlation coefficient is nothing more and nothing less than the square root of R squared. The square root of 0.6466, which is equal to 0.8041. Okay, another linear one here. From a visual inspection, does it seem like the line is a reasonable fit? Yes, the line is right in the middle of the cloud of points. Right, if we were to do this, there's almost the same number of points on this side as there are on this side. Write the equation of the regression line for predicting the length from height. So the expected length is equal to the intercept. So when when height is negative, then the intercept is somewhere over here, right? 470.66 plus 3.92 times the height. Estimate the predicted mean of the length of the equatorial height 180, so we just plug in 180 here times 3.92, which is equal to, and then we're equal to something. I don't have my calculator with me. Plus 470.66, which is equal to 1,176.26. So that's how you do it. You plug in for every 1 centimeter. For every 1 centimeter change in height, you're going to have a 3.92 centimeter change in length. All right. Describe the relationship between the number of calories and the amount of carbohydrates in grams. Positive, moderate. Okay, and it's linear. In this scenario, what are the explanatory and response values? Explanatory, calories, response, carbs. Okay. Why might we want to fit a regression line to these data? Well, we can predict the amount of carbohydrates given a number of calories. And so if we can have calories, we can then say how many carbs would be in there, right? We don't need to know the exact number of carbs. Do these data meet the conditions required for fitting a least square lines? No, because in the residuals, this one, remember, it has to be nice and straight, and it looks like a V shape there. And so the constant variability assumption is violated. So the variability here is not constant. And you can kind of see that, right? You can kind of see that this is a variability here, and over here is huge. And it translates to this. And last but not least, what is the estimated model equation? Here it is that the relative orange expected relative orange is equal to 0.037 right there, plus beta 1, 0.051 multiplied by what? The MLH. Okay. What is the predicted mean relative orange area for a guppy that is heterozygous at 8 out of 9 low C? Okay, so you just MLH, you just replace that with 8 out of 9, and you solve for this. Okay, and that is about 0.0113. Sorry, no, 0.0823. Based on the linear model, how much does the mean relative orange area differ between a guppy that is heterozygous at 2 versus 4 out of 9? Right? And so you just plug in, you would just plug in first 2 out of 9 and get that number, and then you plug in 4 out of 9 and get that number, and find out what the difference is between the two, and according to the key, it's 0.0113. Alright, conduct a hypothesis test to determine whether relative orange area is significantly associated with MLH. And so your null hypothesis is that beta 1, this right here, beta 1 is equal to 0. And your alternative is that beta 1 is not equal to 0. How do we test it? We look at the t statistic, 277. We look at the p-value less than 0.05. So p-value less than 0.05. So in that case, we reject the null and go with the alternative, meaning that the slope, this number here, the MLH, this number here, is not equal to 0. And so you go with that. So MLH is a significant predictor of the relative area of orange spots. All right, and then you compute the 95% confidence interval. Remember, that is your your value, your expected value. Plus, minus your 95% confidence t-score, your critical t, multiplied by your standard error, the sample mean. You have everything for that here, right? You have the number, you have the t, you have the p's, so the user freedom, so your n is 146, I think. So anyways, your confidence interval is 0.015 to 0.087. And the reason why I say I think is because I need to check to see if what they're using for the t. T is usually n minus 1. So that's what I'm going to go with. And so we're 95% confident that the true relative orange area is between 0.015 and 0.087 based on this sample of guppies. Okay? Or, the population mean increase, the relative increase in relative orange area with 1 unit of MLH.